Hello and welcome to lecture 23 of the course Theory of Computation. In lecture 22, we started to discuss the equivalence of context-free grammars and push-down automata. In this lecture, we continue the proof of the same fact. Right? So, we stated the following in lecture 22. Right? One is that the main theorem is that a language is context-free if and only if some PDA recognizes it. And then we proved lemma 2.21, which is one direction of the above theorem, which is that if a language is context free, there is some PDA that recognizes it. We completed this proof by given a context free grammar, we explained how to construct a PDA that is equivalent. Right? So that's how we proved lemma 2.21. So that goes that constitutes one half of the proof of theorem 2.20. Right? Theorem 2.20 is an if and only if statement, so it needs both directions of the proof. Right? So what is the next direction? The next direction is says that if there is a push-down automata that recognizes a certain language, then that language is context free. Right? So that completes. So this is lemma 2.27. And lemma 2.27 and lemma 2.21 together constitute the proof of theorem 2.20. Right? So these two together constitute the proof of theorem 2.20. So what we now have to show is that if a PDA recognizes a language, then that language is context free. Right? So okay. So the way we do this is a kind of natural thing. If there is a PDA that recognizes a certain language, right? So there is a PDA. So given the PDA, we will explain how to come up with a grammar such that this grammar will be equivalent to the PDA. Meaning any string that is accepted by the grammar will be accepted by the PDA, and anything that is not generated by the grammar will not be accepted by the PDA. Right? So this will be equivalent. It will be exactly the same set of strings that is accepted by the PDA, which will be generated by the grammar. Right? So that is the kind of high level picture of what we are going to do. So now let's get into the details of the same. Right? So the first point is that if you recall in the last lecture of week 4 and lecture 21. Right, we immediately after seeing PDA, we had explained couple of things. One is that any PDA can be given any PDA, if it has multiple accepting states, you can construct an equivalent PDA which has a single accepting states. So you may recall that this was merely by if it has multiple accepting states, you add a new accepting state and you make epsilon transitions from all the old accepting states to the new accepting state. Right? So that's how we did the first one. The other two facts that we said is that given a PDA, we can construct an equivalent PDA that always empties the stack before accepting. Right? So if the original PDA, if it did not empty the stack before accepting, we can construct an equivalent PDA where we can force it to empty the stack before accepting. Right? So this involved putting some symbol at the beginning of the stack and then ensuring that symbol is removed before it is accepted. Right? And the third thing is that we can ensure that every transition involves a push or a pop, but not both. Right? So basically we are saying that every transition either pushes into the stack or pops out of the stack, but does not do both. Right? So there will not be a transition of the type which does not touch the stack at all. There will also not be a transition which does both push and pop. So every transition that you take will have a push or a pop, but will not have both. Right? So now because we saw these things in lecture 21 and we explained how we can accomplish this, we will be using these things. Right? So the task is to construct a grammar that is equivalent to a given PDA. Now that we have told or we have seen how any PDA can be converted into a PDA with these properties, we may as well assume that the PDA that accepts the language also satisfies these properties, right? So the given PDA, we may assume that it satisfies these properties, meaning it has a single accepting state, it empties the stack before accepting, and every transition has a push or a pop. Now, from such a PDA, we will construct an equivalent grammar, right? So, what are the strings that is accepted by this PDA? These are the strings. So, there is a starting state to the PDA, right? And let us say there is a starting state, let us say Q start, and there is an accepting state Q accept, right? And something like the strings may traverse somehow and finally reach Q accept. So, what are the strings that take the PDA, that the PDA can read from the starting state, or that the PDA can read so that it can move from the starting state to the accepting state, right? So, this is what we want to know. What are the strings that can take the PDA from the starting state to the accepting state? And because, so you notice that I said the accepting state, right? So, we are already making use of the fact that the PDA has a single accepting state, right? If it has multiple accepting state, then I cannot say the accepting state, it may not be a unique one, right? And because of property 2, we can assume that the stack will be empty when we reach the accepting state, right? Because we assume property 2, we can say that the stack will be empty, right? So our goal will be to identify the strings that can take the PDA from the starting state to the accepting state, and when it takes it to the accepting state, the stack will be empty, right? Of course, when you start processing also, the stack is empty, right? When the PDA does not come or does not begin operations with a filled stack, right? So this is the key thing here, right? We want to know which are the strings that the PDA can read, which will allow it to move from the start state to the accepting state, and when it is reaching the accepting state, the stack will be empty. Okay, so this turns out to be quite convenient in the construction that follows, right? So what our main thing is going to be so now the goal is to construct a grammar such that the grammar should generate all these strings that take the PDA from the start state to the accept state, right? So what we will do is, in general, we will have variables of this type, a, p, q, right? Small p, small q, and this variable of the grammar, we will construct the grammar in such a way that this variable will generate all the strings that take the PDA from the state P to the state Q. Okay. APQ we will construct in such a way that we will construct the rules of the grammar in such a way that APQ will generate all the strings that can take the PDA from the state P to the state Q, keeping the stack empty or with an empty stack. So the stack, when it takes it to the stack Q, the stack will be empty, right? So again, more formally, I'm writing it here. This is the set of all strings. It's the same thing that I'm saying again. All strings that take the PDA capital P from P the state P and empty stack to the state small q and empty stack, right? So this will be the set of all strings, right? So maybe I'll just draw a small picture, right? So suppose this is state P, let's say the stack is empty here, and you want these strings that can move from the state P to state Q. But notice this, so which means from empty stack to empty stack means maybe something gets added into a stack and finally those gets removed, right? Which means if the stack had some content here, let's say I'm just denoting by the shaded area, if a string can take the PDA from P to Q on empty stack, it can also take from P to Q while retaining the contents of the stack, right? But because how does empty stack to empty stack happen? Because it cannot pull out anything from the stack. Instead, it will push some things, and by the time it reaches Q, it retrieves those things. So suppose the stack was not empty; it had some content. Let's say some string called K or something, right? So now keeping the string K there, now it is the same set of transitions. If you take, it will put some things into the stack, right? So originally it could take from empty to empty. So the K will be there and it will put some things in, and then it will remove those things. And when it reaches Q, whatever was put would have been removed. So empty stack to empty stack also means that it can retain whatever the stack contents were, right? So this is something that will become relevant later. So right now I'm just defining it as those strings that can take the PDA from the state P with the empty stack to the state Q with the empty stack, right? But what I'm remarking is that these strings also take from state P to state Q while retaining the stack, right? So maybe I'll just remark here. These strings also allow the stack to be retained. Right. So APQ also can be interpreted in this manner, right? So now, so this is going to be for all any state P and any state Q, including where P and Q are the same. So now consider the variable A subscript Q start and Q accept. What are the strings that take the PDA from Q start, the starting state, to the accepting state while retaining the stack or while keeping the stack empty? This is exactly the set of strings that are accepted by the PDA, right? So that's what I am written here. A Q start comma Q accept basically should generate those strings that are accepted by the PDA, right? So what we will do is that we will set this variable A Q start Q accept. We will set this as the starting variable, because what is the language generated by the grammar? It's the language set of strings generated by the starting variable. So this will be our starting variable, and this is the key thing. The variables are all the variables of the type APQ, and AQ start Q accept will generate those strings which are accepted by the PDA, and that's what we want, right? Okay, so now let's try to understand the rules, right? So we have just told what the variables are. So now we need to define we need to set up the rules of the PDA, right? So let's consider what happens when we move from a state P to a state Q, right? So, so when you're moving from a state P to the state Q, let's say we start with the empty stack, and so that's what the definition is, right? P comma empty stack to Q comma empty stack, right? So there are two possibilities, right? So let's see what happens. So initially you are in state P with the empty stack, and state P with the empty stack, and the next move from there, we know that every move has a push or a pop, right? So the next move from here must involve a push, because there is nothing to pop, right? So the next move involves a push. Let's say it puts some symbol, let's say R or something, let's say L or something into the stack, right? And let's consider what happens. So and at the end we need to go to state Q with the empty stack. Now what would have been the last move that took us to Q? We know that every move has a push or a pop. It could not have been a push. The last move would not have been a push, because if it was a push, this stack will not be empty, right? So the last move has to be a pop. So some symbol, let's say K or something was there, that was removed, right? So there are two possibilities. One is that the symbol that was pushed in the first move, L, is exactly the symbol that was popped at the end, right? The last, so whatever, so which means the stack, whatever we put at the beginning, now you kept putting things on top of it, maybe removing some things, etc. But we never touched the first symbol that was put, right? So maybe I will just maybe I'll just create some space here. Right. So what I'm saying is there are two possibilities. One possibility is that, so the first move you put something in, right, and then the stack put some things, and finally, so here you are at state P, and at the end you are at state. This is the stack contents, stack depth or stack height or something you can call it. Okay, so maybe it doesn't have to be like this, but it could go up, but it never empties in the middle, meaning the first symbol that you put, let's say K or something, that, or L or something, that is never getting touched, right? So this is one possibility. Another possibility is another possibility is this possibility 2. The first symbol that we put, let's say K or L or something, something happened at some point, you pop it. So if you pop the first symbol that you put, then basically at some point the stack becomes empty. And so maybe let's say at some state, at that time we were in some state R, and then again you do something, and finally the stack again becomes empty, which means some other symbol, the first symbol that we put was removed in the middle, and then again some things got put, and even those things got removed. That's why you moved from empty to empty and again to empty, right? So these are the two possibilities. So the red one and the blue one. So first we will consider the red one, and we will try to create a rule that sort of corresponds to this situation, right? So that's what I have written here. The last move pops the same symbol that was pushed in the first move, right? That's what I have written here, right? Which means the stack never got empty in the meantime. It always it was always non-empty, right? So now consider a string. So basically this rule, so it may not be immediately clear, but this rule is kind of corresponding to that, right? So consider a string in APQ. So remember a string generated by APQ, right? Sorry, APQ is a set of, so here I am writing it as a set, but it's a variable, right? So okay, so now for this particular situation, right, we add a rule like this. So where APQ derives, or APQ yields this following thing. The rule is APQ yields ARS B, where A is a terminal, right? A is a terminal, B is a terminal, or so A and B are where A comma B are, it could be terminal or it could be empty also, right? And if you basically you are able to read the symbol A and go to the state R, and then go from then you have the variable ARS, and then you from S you are able to read the symbol B and then go to the state Q. So basically we are saying what is the state in the next step, let's say it's R, and what is the state in the last step before Q, let's say it's S. So basically what you're saying is the first symbol that was pushed here from P to R was something. While we push that symbol, let's say the symbol that was pushed was T, right? While we push that symbol, we read the input symbol A, and now at the end we are again popping the symbol, right? From when we move from S to Q, the first symbol that we pushed, and that happens while reading the input B, and which means from R to S, whatever was the stack, that single symbol, we never touched that, right? So the remaining part of the middle of the string took the PDA from R to S while keeping the stack intact, meaning whatever was already there in the stack, it retained it, which means that it can also take the PDA from R to S with an empty stack, right? And this is the first type of rule, and the second type of rule is corresponding to the blue part over here, right? This one, where the stack gets empty. So for that we add the following type of rules, where for every three variables A, P, P, Q and R, we add the rule APQ derives APR and ARS, APR, ARS, right? And we for all triplets of rules, states P, Q and R, there is an error. RQ, right? It's ARQ, so not ARS, because there is no. So for all triplets of states P, Q and R, we define this. So maybe I'll just say it a bit more formally here, and this is the intuition. So the intuition I wanted to convey before that. So more formally, suppose there is a PDA, right, with a single accepting state, right? So notice that we are able to write a single accepting state because of the normalization that we refer to here. P has a single accepting state, right? And we are able to say that these things, right, like the first symbol, first move should be a push because of the second condition, right? Because we are insisting that every move has to be a push or a pop. Otherwise, the first move could have been nothing, right? Right. So the variables are all of the type APQ, right? And the start variable is AQ0 Q accept. So instead of Q start, I am just using Q0, right? And the rules are this. Okay, so once again, let me explain. For any four states PQRS, right, and T in the stack alphabet, right? So T is a symbol in the stack alphabet, right? And A, B are in sigma subscript epsilon, which means they could be symbols of the input alphabet, not stack alphabet. They could also be empty strings. So what are we saying here? We are saying that if RT is in delta PAE, meaning you have the input, okay, so the next symbol from the input is A, right, and something else, and you are in state P, okay, so you are in state P, so you are able to read A and move to state R while pushing T, and you are popping nothing, so right, so epsilon is popped. So basically from empty stack you will go to a stack with a symbol T. If this is a rule, and the next part is if Q epsilon is in delta SBT, meaning from the state S you are able to pop T and go to Q, and you have read some parts of the input and the symbol that you are now reading is symbol B, right? And you are able to move from basically you have, let's say you have T in the stack, you want to remove the T in the stack. Basically you are popping T from the stack, right, and you are pushing nothing. Then if both of these things are satisfied, if you can go from P to R by pushing T and reading symbol A, and you can go from S to Q by popping T and reading symbol B, then you add this rule. APQ gives ARS B. Notice that PQRS need not all be distinct. A and B could be empty strings, small a and small b, right? But T cannot be empty string because every move has to have a push or a pop. Right? T will not be empty, right? So this corresponds to the case where the symbol that we first push is popped at the end. Once again, if you are able to move from P to R by reading the symbol A from the input and pushing T into the stack, and you are able to move from S to Q by popping T from the stack and reading B from the input tape, then you add these rules of the type APQ gives small a ARS B. So that's the first set of rules, and that you have to do for all the possible quadruples PQRS. Whenever we are able to identify such, we have to see whether these rules are there. This, if we can say that RT is in delta PAE and so on, then we add this rule. The next set of rules are simpler because there is no condition to be checked. For any triplet of states PQR, right, again including the case where they are not distinct, we add the rules APQ gives APR ARQ. So it's straightforward. APQ gives APR ARQ, right? We add these rules for all the triplets PQ and R. And finally, if you notice, if you just have these two type of rules, right, the type 1 and type 2 that I mentioned, you notice that every rule has a variable in the right hand side, right? The starting variable was AQ0 Q accept, and all the rules are of this type, right? It has a variable in the right hand side, so it is never going to generate a string that is entirely of terminals. So you need to have rules where somehow there is no terminal in the right hand side, or somehow we have to eliminate the terminal, no variable in the right hand side, or we have to eliminate these variables. So for that we add these rules for all the states P in the PDA. We add a rule APP goes to empty string, right? So notice that this so the third set of rule, it is consistent with what we want. We wanted the rules APP to generate all the strings that can take the PDA from state. So APQ, we wanted APQ to be the set of all strings that can take the PDA from P to Q on an empty stack. So empty string takes the PDA from P to P on an empty stack, right? It trivially does it, right? Empty string means it reads nothing and you don't make any move. If you are already at an empty stack, you will continue to be at an empty stack. So that way, this is kind of a base case, right? So this completes the construction, and so the way we have constructed it perhaps may not be immediately clear that this generates a the grammar that is constructed in this manner is equivalent to the PDA, right? So we want to show that for all P and Q, APQ generates a string X, right? APQ generates a string X if and only if X can take P from the PDA P from the state P with an empty stack to the state Q with an empty stack, right? So that is, once we show that, the rest becomes clear, because if we show that for all the states, all the variables APQ, we want to show that APQ generates a string X if and only if X can take the PDA from P and empty stack to Q and empty stack. If we show this, then it follows that the starting variable AQ0Q accept, right? This generates all the strings that can take from the starting state to the accepting state on an empty stack, which means that the set of strings accepted by the PDA is equal to the set of strings generated by the grammar, right? So this is the key thing that we have to show from now on in order to prove that this construction results in a grammar that is equivalent to the PDA, right? So this again, in fact, we are in one direction of the proof of the theorem. Now we are again in a situation where we have to prove this equivalence, that the constructed grammar is equivalent to the PDA, or the constructed grammar, this variable generates exactly the string that we want. So what we will do is to show the following two claims, right? The first claim is that if APQ generates X, right, then X can take the PDA from P with an empty stack to Q with an empty stack, right? So this is one direction, and the other direction is that if a string X can take the PDA from P with an empty stack to Q with an empty stack, then APQ generates X. So together these two claims will prove what will prove this highlighted sentence, right? The part that I am highlighting now. APQ generates the set of all strings that can take the PDA from P to empty stack to Q to empty stack. So claim 2.30 and 2.31 together will prove this. And since I think we are kind of over the prescribed time limit, we will show the proofs of 2.30 and 2.31 in the next lecture. So just to summarize what we saw, the goal was to prove the direction of the proof, which says that if PDA recognizes a language, then that is context free. The approach to proving it was to construct a grammar given a PDA. So we assumed there some normalizations which we had shown that was possible for any PDA, namely PDA has a single accepting state, PDA empty stack before accepting, and every transition involves a push or a pop, right? But not both. And the grammar involved variables APQ, which were corresponding to those strings that can take the PDA from state P with an empty stack to state Q with an empty stack. And we constructed the rules of the grammar, and now what remains is to show that the variables APQ indeed generate exactly those set of strings that are desired, and that will be proved by the following claims 2.30 and 2.31, and this we will see in the next lecture. So see you in the next lecture.